So today we're going to talk about the internal structure of the sun. So last time we gave an introduction to the sun and how much power it emits, what composes it, and then we got into the proton-proton chain discussing exactly how our sun generates its energy. So if you haven't already seen that video, make sure to go back and see that first. So before we get to discussing the structure of the sun, you need to take out a half sheet of paper for a question of the day. So in this case, we don't care if it has the weasel toes on it, since this isn't actually going to be graded, except by you, but it's not going to be recorded. So hopefully you are ready to begin. So when you are ready to begin, you can unpause this video. If you're not ready, then you can pause it. So hopefully you're ready to begin. So what you need to do right now is write down the steps of the proton-proton chain without looking at your notes or any other resources, and try to clearly distinguish between these steps. In other words, one line per step. So you're going to have 90 seconds for this. So at this point you can pause this video, and after 90 seconds have passed, or after you have completed it, hopefully whichever comes first, then you can unpause this video. So hopefully now you have completed the question of the day. If you're watching this video with somebody else and you've both done this, then trade papers with each other. So here is what you should have. The first step of the proton-proton chain, you have one proton colliding with another proton to create a deuterium nucleus, and also a positron and a neutrino. So one check for each of those. And you could have other symbols in place of a couple of these. For example, instead of H1 or H11, you could call it H1 with a superscript 1 on the left side, or you could just call it P+ for the proton. Because after all, it's not actually an atom, it's in the center of the sun. Everything's lost its electrons. And similarly, for the deuterium nucleus, you could just call it a D+. D+ is the symbol for a deuterium nucleus. That is a bound state of a proton and a neutron. But the positron should probably look like E+. You don't necessarily need the 0 and the 1 here, but calling it E+, you definitely need that for the positron. And your neutrino. Technically it's an electron neutrino, but you can give yourself the plus even if you forgot to include the subscript here. But the fact that it's an electron neutrino is going to have important consequences for our discussion today. The next stage, you have that deuterium nucleus plus a proton yields a helium-3 nucleus plus a gamma ray. So for these last two checks, you definitely need to have helium-3 here. So in other words, either He-3 or He with a 3 subscript, and you also need to have the gamma ray there as well. After all, that's the energy here. In the previous step, the only energy that was emitted was in the form of what's going to be emitted when this positron collides with an electron, when it produces the 2 gamma rays, and the energy of this neutrino. But that particular energy doesn't really go much to causing the sun to shine because that neutrino escapes. Finally, there is the third step. You have one of these helium-3 nuclei. It collides with another helium-3 nucleus, and that creates a helium-4 nucleus plus 2 protons. That is 2 hydrogen-1 nuclei. So if you had that in place of this, that's perfectly fine. It's the same thing. So tally up however many you got correct, write that number at the top of your paper over the number 14, and just hold on to this or do whatever. If you didn't do very well, then maybe go back to the beginning of this video and try again. So now we're going to go back to what we're going to talk about with our sun today. So in terms of understanding our sun's structure, and for that matter what's going on with stars in general, you need to understand a concept called hydrostatic equilibrium. Long story short, hydrostatic equilibrium is achieved when there is a balance between the outward push of gas pressure and the inward pull of the force of gravity. So you just imagine a little blob of matter in here. When the outward force of the pressure is balanced by the inward pull of gravity, hydrostatic equilibrium is attained. If that's not the case, if pressure is greater, then this little blob will end up moving outward. Or if the pressure is less, then the blob will end up moving inward. And a lot of times in a star, both of these are occurring at different places at the same time in the form of convection. So we're also going to address that today. So first, when the weight of overlying material increases, which is what happens when you move inward, the temperature is also going to increase. For example, you can find via a calculation, and for that matter, from the results of observations, that the internal temperature of our sun is close to 16 million kelvins. And in fact, it's the inner 10% of our sun's radius that's responsible for the great majority of our sun's nuclear fusion. So you can kind of see that in this chart, which is generated with a computer simulation, and it's also corroborated by observations from helioseismology, which we'll get to soon. But the inner 10% accounts for about 40% of the luminosity of our sun, and that's again where the temperature is very high. And then by the time you get to 30% of our sun's radius, all of our sun's luminosity is accounted for. In other words, every single bit of energy is produced in the inner 30% of our sun's radius. So, as we mentioned in the previous video, this actually leads to another independent way of calculating our sun's age. For example, when you consider the conditions that occur at our sun's surface and the results of various helioseismology measurements, we find that the core of our sun is actually only about 34.1% hydrogen. In other words, most of the hydrogen in our sun's core has already been converted to helium. So when you go through that calculation based on integrating our sun's likely luminosity over time, you find that our sun is somewhere between 4 and 5 billion years old. In fact, to be more precise, the calculation yields a result of 4.5 billion years plus or minus about 300 million years, so about 4.5 plus or minus 0.3 billion years old. So it's, again, nice to have a completely independent means that corroborates our understanding of our solar system's age. Now, how is this energy that is manufactured in our core, the core of our sun, transported? So out at the edge of the core, there is a large radiation zone, and that radiation zone starts to extend outward by a considerable margin. What we mean by a radiation zone is that in that region, energy is transported by the process of radiation. In other words, photons actually carrying off the energy and bouncing into other things and everything before they get to the outer layer, or at least the layer outside of that, the convection zone. Now, it turns out that it takes a long time for a particular photon to escape to our sun's surface due to all of these interactions with the radiation. In fact, for a typical photon, it takes about 1 million years. Now, of course, our sun has lots and lots of photons that it's generating by the processes of this nuclear fusion, so that's why it generates generates a lot of energy, and it shines very, very brightly. Now, by the time those photons reach the surface and everything, they're actually composing a black body spectrum. So that's something that we've talked about earlier in the course, the black body spectrum, and it's essentially the same thing that you would get if our sun was just a solid object. Of course, we know our sun is not a solid object, but we would end up getting the same type of black body spectrum if it was, with the exception of the various emission and absorption features in the spectrum. Now, outside of the radiation zone, which is between about 30% of the radius and about 70% of the radius, we actually have what we call the convection zone, the outer region of our sun, the outer 30%. Energy is transported by convection. So what convection is it's a bulk movement of gas, or I shouldn't say gas, but a bulk movement of a fluid. You can actually kind of see convection sometimes if you heat water on a stove and you watch right before the little bubbles start to form. You'll see these kind of convection bulk types of motions in there, and if you're not sure about that, then just do that sometime, and right before it starts boiling, maybe drop a little droplet of food coloring in there, and you'll really see that type of motion. But convection is how energy is transported in the outer 30% of our sun. And finally, once it reaches the surface, which we call the photosphere, radiation lets free. In other words, here you're talking about something that is emitting blackbody radiation, that is the photosphere, the so-called visible surface. Again, of course, it's not a surface. If you went there, you would sink right in and be incinerated. But it's the so-called surface of last scattering. It's the part that we see. So from innermost to outermost, we have the core, the radiation zone, the convection zone, and then the photosphere. So here is a diagram of that. So see the white silver region in the core where the nuclear fusion is actually going on, and then outside of that we have the radiation zone where the energy is being transported by photons carrying away the energy, and then around the convection zone the more efficient energy transfer process is via convection cells, where you have areas of hot gas that end up forming down here, and as they form they end up starting to expand, and expanding they get less dense and they rise, but as they rise they're going to into regions of even smaller density, which means they end up expanding. But what happens as a gas expands? It cools. So finally it reaches near the surface, and when that happens it has cooled and becomes more dense and ends up falling back in, and the process ends up repeating. So it ends up rising up to the surface, cooling, and then going back down, and then getting heated up by the radiation zone, rising up toward the surface, releasing its energy, cooling, etc. And you also have kind of multiple things going on here as well. For example, the other convection near the surface in the form of these granules and all of that, which we're about to see soon. Here is a picture of a sunspot, and here is this granulation that we were talking about. These are little convection cells. They have typical lifetimes on the order of about 15 minutes, and a recent solar telescope just went up that is actually able to take continuous high-resolution images of these granules and create kind of continuous video that's at the resolution necessary to really be able to see what's going on with these granules. So this is kind of a lower resolution picture of this. So just showing a higher resolution picture of our sun using the best available solar telescope, we have this showing the granules in quite high resolution. So you might wonder, is like, well, is there really all that much of a difference between this and this? Like, yeah, the image looks sharper and everything, can see some more details, but is it really all that much better? Well, if you zoom in on the central region here like this, you see that yes, it is a lot better. In fact, the smallest details here, the smallest resolved details here are about 18 miles wide, so about 30 kilometers wide. So when you consider that the radius of our sun is about 7 times 10 to the 5th kilometers, and we're seeing details that are 30 kilometers wide, this is quite an achievement here. Now, another nice little bit of the solar interior that is kind of interesting is a region called the tachocline. It's actually the area that separates where our sun rotates differentially compared with where it rotates as a solid body. So what's the difference? Well, if you imagine just taking a ball and spinning it, all parts of the ball are going to go around in the same time. So what that means is that if one part of the ball takes 2.5 seconds to go around, then every single other part of the ball will take 2.5 seconds to go around once. Now, the tachocline is the area that kind of separates the inner region of the sun, which does rotate as a solid body, from the outer region of the sun, which does not rotate as a solid body. In fact, as we're going to discuss a little bit later, the parts closer to our sun's equator take a little bit less time to go around once compared with the parts that are closer to the poles. For example, the equator takes something like 25 or 27 days to rotate once, and closer to the poles it takes more like 34 days to rotate once. And the tachocline is the area that separates those two. Now, in this graph, the tachocline is illustrated right at this region right here at about 0.68 solar radii, or about 0.67 solar radii. Now this dashed line that you see right here is the division between the radiation zone and the convection zone, which also, interestingly enough, happens to be very, very close to the tachocline. Now, the reason this is significant is because solar storms, which they're caused by interactions in the interior, they are only visible when they reach the solar atmosphere. But you're dealing with interactions having to do with the differential rotation, and this differential rotation, which exists outside of the tachocline, is what ends up bending our sun's magnetic fields around, and that ends up creating the solar storms in the end, as we'll discuss later on. So, interesting physics there. The reason that there is that layer is a phenomenon called convective overshooting, where convection cells, which remember they end up causing the transport of energy in the outer part of our sun, they end up sometimes overshooting the region of where they would be stable. So that area where and similarly as they go down and after they've cooled, they end up overshooting the region where you would think just by a quick physics calculation that they should come back up. Now, the reason this happens is because these convection regions actually have momentum as they are moving around. In particular, when they come down, they are carrying momentum with them, and so it takes longer for them to stop, so to speak, than what one would think. So that means they actually end up entering a region where radiation, energy transfer by radiation, is important, and that is the tachocline, where those two regions actually overlap due to this convective overshooting. We're going to come back to convective overshooting later on because this actually is important, particularly early on in the universe, controlling which types of stars can eventually explode as supernovae. It turns out that because of convective overshooting in stars as they evolve, it could end up lowering the mass, the necessary mass that a star would have in order to undergo a core collapse supernova explosion. So, next, we often wonder, how do we know what is going on inside of the sun? In other words, this is a question that I occasionally get from students because you can't exactly drop a probe in there and directly measure its temperature. Well, it turns out that you can indirectly do almost exactly that through use of solar seismology and neutrino astrophysics. So first, how does seismology work in the case of Earth? So let's say an earthquake occurs. As the earthquake occurs, seismic waves scatter out in all directions, but as they scatter out, they bend. The reason they bend is because the speed of sound changes as you enter materials of different density, different structure, and stuff like that. And as that happens, they end up bending, similarly to how light bends when it enters a region of a different index of refraction. Well, if it suddenly encounters the liquid core, well, then there is a sharp bending. Again, how light very quickly bends as it enters a prism from the air. If that prism has a different medium in it, gradually changing medium, then it'll kind of bend gradually, but if it suddenly changes, you're going to have a sharp bending. So it should also be noted that not all waves do this. Only the P waves are actually able to make it through the liquid core like this. The S waves cannot do that. Neither wave can bounce off of the solid inner core. That's how we know the internal structure of Earth. So there's a reading from a Richter scale. Well, the sun has waves as well, and these exert pressure and create various standing waves in the sun. These can be measured also, and from that we actually have a pretty good idea of the internal structure of our sun. So this actually shows kind of that ringing, so to speak, due to the standing pressure waves that occur in our sun. Now, computer models can make predictions giving pretty precise idea of how our sun's interior structure changes going from the center to the surface, and we've already talked about how these are what lead to our independent confirmation of our solar system's age. Here is a very nice model showing the difference between computer model predictions and helioseismology measurements. And notice, in fact, the the biggest differences are on the order of about 1% in terms of things like density, pressure, stuff like that. And that occurs, surprise, surprise, at the tachocline, where you have that convective overshooting and the energy being transported both by radiation and by convection. So another cutaway diagram showing paths of sound waves in our sun's interior, and these are the types of things that can be measured. Now, interestingly, we have a very nice understanding nowadays of how our sun generates its energy in accordance with the theory that was made back in the late 1940s, early 1950s concerning the proton-proton chain and how much energy that generates and being able to potentially be measured. And in particular, that actually predicts the existence of, well, predicts that we should be measuring neutrinos that are being created in this process. Remember, the first step of the proton-proton chain says that there is an electron neutrino being produced each time that happens. Well, you can make a calculation of how often that should be occurring based on our sun's luminosity, and therefore how many neutrinos should be reaching Earth, and based on understanding how neutrinos interact with the weak nuclear force, how often we should be able to measure them in our detectors. And it turns out we were only measuring about 1/3 of what you would expect. But based on how confident we were with our computer models in understanding the interior of our sun, which is actually relatively easy to model with computer models, scientists were fairly confident in being able to make a bold new prediction that it was actually the computer models that were correct and our understanding of neutrinos and how they would interact that was wrong. And it turns out that the solar physicists were right. So, what are these neutrinos? Well, neutrinos, they were originally predicted to exist back in 1933 by Wolfgang Pauli, the same person after whom the Pauli exclusion principle from chemistry class is named, that says that you can't have two electrons in exactly the same quantum state, the Pauli exclusion principle. And the idea is that, well, a neutron by itself is unstable. Neutrons had just recently been discovered, and it was found that they decay into protons and electrons with a lifetime on the order of about 11 minutes or so. But a proton and electron, well, the total energy of those was not enough, and plus their kinetic energy was not enough to account for the mass of the neutrino. So it also would seem to violate conservation of angular momentum, because the neutron has a known quantum spin, so to speak, which is kind of a fundamental unit of angular momentum, and the electron and the proton also have that unit of spin. But if it was just a neutron decaying into one of those, I'll just say that each of those has spin 1/2, and the neutron also has spin 1/2, well, that wouldn't seem to be kosher. In other words, there should be a third particle that is also a, quote, spin 1/2 particle that should also be carrying off some of this angular momentum to make everything work out. So it turns out that was correct. There is such a third particle that also carries off a little bit of energy as well, and that was the neutrino. That was not discovered until the 1950s. Now, neutrinos only interact via the weak nuclear force, so they do not interact with the electromagnetic force. That doesn't mean they don't interact with electrons, because there can be kind of some little weak interactions there, but they do not interact with the electromagnetic force, which means that while these photons and electrons and everything are bouncing around inside of the sun, these very dense, hot conditions, once a neutrino is produced, it just zips right up to the surface. It takes 2 seconds to do so. It travels at about the speed of light. In fact, as far as we can tell, it travels at the speed of light. Those we're about to see, we do have some very good reasons to believe that it must travel at a hair less than the speed of light. But it's really difficult to say, because neutrinos are very enigmatic particles, and there's still a lot about them that we don't quite 100% understand. Now, in any case, based on the rate at which neutrinos are being produced in the proton-proton chain, you expect that about 35 quadrillion solar neutrinos are passing through your body every single second, and this happens even at night. So they don't really do anything to you, because they just pass right through. Again, they don't interact with the electromagnetic force. They only interact with the weak nuclear force. So they just zip right through you. So how are we to detect these things? So here's what was done by a physicist named Raymond Davis. He devised an experiment to look for solar neutrinos. He made a tank containing 100,000 gallons of cleaning fluid that is carbon, I've heard it said as carbon tetrachloride, but tetrachloroethene if you prefer. This chlorine atom actually can interact with the weak nuclear force via a neutrino. In particular, what happens is you have the chlorine nucleus interacting with a neutrino to create an argon-37 nucleus and the emission of an electron. So this is kind of a sort of radioactive decay in a way. It's a nuclear interaction at least. And here's the picture of this experiment, the setup in the home state gold mine. And these detections occur very rarely, but nonetheless, based on our understanding of the weak nuclear force and these particular nuclei, we can predict how often we should be able to detect an atom of argon. And it turns out you should expect such a thing about once every day. But it turns out we only got one about once every 3 to 4 days. So that seemed a bit strange. Well, again, the solar physicists were very confident in our understanding of our sun, and we predicted that something else must be going on here. Now, in terms of understanding this, some ideas were put forward, and one of the big ideas was that neutrinos oscillate. That is, they oscillate into other types of neutrinos. In particular, remember that E subscript on the neutrino in the proton-proton chain? That's an electron neutrino. It's what's produced when you have weak nuclear interactions involving electrons and everything, but it is not something that would be directly associated with other particles that are similar to electrons. In particular, I'm talking about other subatomic particles called muons and tauons. And muons and tauons are unstable, heavy relatives of electrons, and when they decay not just into their lighter cousins, but they also have these other neutrinos. For example, when a muon decays, a muon will decay down to an electron, but it will also emit an electron antineutrino and will emit a muon neutrino. This is all involved with conservation of lepton number and muon number and electron number and all that. So there are these various conservation laws that must be obeyed. But the point being here is that there are several different types of these leptons, so to speak, the electron being the lightest, the muon being the next, and the tauon being the heaviest, each of which has its associated neutrinos. And the theory was that these neutrinos could potentially oscillate between each other through something known as the MSW effect, the last name being of each of the people who went into this, going into that acronym, MSW, and in particular the last one, the W, is a cool name. The whole thing, MSW, is the Mikheyev-Smirnov-Wolfenstein effect, by which neutrinos could potentially oscillate into other flavors of neutrinos. But this would only happen when they are interacting with other matter. In other words, it's not going to happen when they're traveling in space, but in the interior of our sun, they could potentially oscillate. Or when they are in Earth, they could potentially oscillate. This makes two predictions. And by the way, one of the early people to come up with this as a possible explanation for the lack of solar neutrinos in the home state gold mine experiment was none other than Hans Bethe. He came up with this explanation in 1986. He published it. He did this at the age of 80. This is the same Hans Bethe who in the 1920s was one of the astrophysicists who proposed that our sun is getting its power by nuclear reactions, converting matter into energy in the core. So the same Hans Bethe who proposed that in the 1920s, which turned out to be correct, is also the same Hans Bethe who predicted that this could be an explanation that this MSW effect could be an explanation for the lack of solar neutrinos in the 1980s. So he was a very prolific physicist throughout his life. He continued publishing all the way up to his death at the age of 98, I believe, in 2005. So, in any case, the idea is that these neutrinos oscillate, but the home state gold mine experiment was only capable of detecting the electron neutrino, because going back to this interaction, it is the electron neutrino that would have this resonance between the chlorine-37 nucleus and the argon-37 nucleus. But muon neutrinos and tauon neutrinos would not do this. So instead, another experiment was devised using heavy water, ultra-pure heavy water, that is D2O, where each hydrogen is instead a heavy hydrogen, that is a deuterium nucleus. Well, it turns out that the deuterium nucleus, which again has a very large nuclear cross-section, it likes to interact with all kinds of neutrinos, not just electron neutrinos. So if the neutrinos are oscillating, then the heavy water experiment should be able to detect the expected number of neutrinos. So here's kind of the inside of that. And it turns out that this is exactly what ended up happening. The Super K experiment, as it's called, actually did end up detecting all of the types of neutrinos, the electron, muon, and tauon neutrinos, and this showed two things. One, our sun operates in the interior exactly how we expect, and two, neutrinos oscillate. In fact, I should add a third thing. A corollary of the second thing, the fact that neutrinos oscillate, is that neutrinos must have a small non-zero mass. And as far as we can understand, that means that these neutrinos must not travel at exactly the speed of light. They should travel at a hair less than the speed of light. So that, again, makes neutrinos very enigmatic particles. They are massive particles that nonetheless travel extremely close to the speed of light and seem to exert very little energy and momentum when they interact with things. Now, next, we need to talk about the solar atmosphere. So we've already talked about the four parts of the solar interior. We have the core. Outside of that, we have the radiation zone. Outside of that, we have the convection zone. And then outside of that, we have this photosphere. There are two more layers, and those compose the solar atmosphere. Now, this photosphere, again, that's what we actually see. And you could kind of consider this somewhat part of the solar atmosphere, but it's the border between the interior and the atmosphere. But again, it's the part that we actually see. In fact, the majority of the light that reaches our eyes actually comes from a region that's only about 100 kilometers thick. Remember, our sun is about 700,000 kilometers in radius. Now, the photosphere itself has a blackbody spectrum with an average temperature of around 5,800 kelvins. So when you take very close images of that, again, you can see those granules that we showed in that previous slide, and those are little convection cells that transport their energy into the photosphere. Now, this is our sun's actual spectrum superimposed onto a red blackbody spectrum. Again, notice that this is a log linear plot, but the reason that there are differences here is because, well, remember our sun's photosphere is composed of gas, and that gas can undergo atomic transitions. It can absorb and it can emit. So it's not a perfect blackbody, but it's a darn good blackbody. So here's kind of how this granulation works. You have these little convection bubbles coming up toward the surface, then they spread out, releasing their energy, and then fall back. Notice that when they fall back, they are cooler, which is why these areas are darker. In fact, here's one of those areas between two granulation cells. Now, these granules are actually relatively large. Here they are compared with the size of Earth. And then you have these sunspots, which are even bigger. Some of these sunspots will be bigger than Earth. We're going to talk about those in just a moment. So again, these granulation cells and a sunspot. And you can look over that as well. Now there's also a nice phenomenon called limb darkening. When you look at the limb, that is the edge of our sun, you end up, it looks darker. So here's how that appears. I stole this image from an observatory site. In fact, this is one that can be used in a little solar lab. But notice that around the edge, it's darker compared with the middle. How do we explain that? Well, here's the idea. We have the solar atmosphere, and the solar atmosphere has some thickness to it. So when you're looking straight toward the middle of the sun, your line of sight is only going through, well, the thickness of the solar atmosphere. But when you look toward the edge, that is the limb, your line of sight is going through more than just the thickness of the solar atmosphere, because it's going through at an oblique angle. So there's more attenuation of the light there, which is why the edge looks a little bit darker. Now, the other layers of our sun, outside, that is the atmospheric layers outside of the photosphere. First, outside of the photosphere is the chromosphere. It's a very thin layer of hot, low-density gas. It has a temperature of about 10,000 kelvins, and it emits an emission line spectrum. So remember, a hot, diffuse gas will show emission lines in the spectrum, because you're talking about atoms that are more likely to be energetic enough that their electrons are in excited states, and therefore more likely to decay down to ground states and emit photons. So that's what you're dealing with in the chromosphere. So yeah, the temperature is going up there. And then outside of that, you have the corona. The corona is very hot. We're talking about temperatures of 1 to 2 million kelvins. Remember, the photosphere, which was the part we see, surface of our sun, so to speak, has a temperature of about 5,800 kelvins. But the corona is much hotter, but it's also much, much more diffuse. So here, we're talking about atoms that are so energetic that they're dealing with X-ray emission at times. And the corona stretches out to about 20 solar radii. This is actually the part that you see during a total solar eclipse when our moon is blocking the line of sight to the sun. Now, how it's getting its energy, we now recognize that this is probably due to what we call little nanoflares. So I don't want to talk too much about these now because we kind of need to discuss solar flares, but basically there are little bits of kind of magnetic reconnection events that end up carrying a whole lot of energy out into the outer part of our sun. But again, we're going to discuss that at a later point. But suffice it to say that, yes, the solar corona is very hot, but because it's so diffuse, that means we can really only see it during a total solar eclipse like this. So there's our moon covering the sun, but the white area actually is the solar corona. Notice that the nice lines here, these lines are occurring because of our sun's magnetic field, just as iron filings end up taking a nice little shape when you drop them around a bar magnet. Well, the charged particles around our sun and everything, particularly solar corona, solar chromosphere, they end up also being shaped by our sun's magnetic field. So, if you want to learn a little bit more about the solar corona, there are a number of articles out here. There's a little video that you can click on with the link here in the actual PowerPoint. Now, sunspots. What are these? Are they holes in the sun? They're not holes in the sun. Instead, they are regions on the surface with a cooler solar temperature, with temperature between about 3,000 and 4,500 kelvins, again, compared with the typical surface temperature of around 5,800 kelvins. And remember, intensity goes as temperature to the 4th power for a black body. So if you make your black body half as hot as in the case of this 3,000 kelvins bit, that means it's only 1/16 as bright. So it's going to look noticeably dimmer. In fact, when you use the right filters, it can look quite dark. But if you look at it in unfiltered, it'll just look a little bit more orangish compared with the rest of the sun. So here's a picture of a group of sunspots. And here's another picture of a sunspot taken just with visible light around sunset through a palm tree. So in general, looking directly at the sun is not recommended, but sometimes in optimal conditions around sunset, it can be done, and this is how sunspots have been observed for several thousand years now. So here's that calculation. A typical average sunspot temperature is going to correspond to only about 1/6 as much energy, and that's going to produce a noticeable difference in brightness. So why is it there? Well, they occur where our sun's magnetic field is particularly concentrated, and one of the laws of physics is that charged particles get deflected by magnetic fields. So if they try moving through magnetic fields, in particular if they try going perpendicular, they're going to get deflected. As a result, less energy is going to reach the surface because the charged particles carrying some of that energy are going to get deflected away from those regions. Now, this is one of Galileo's drawings of the sun, and again, even ancient Chinese astronomers also knew about sunspots, but Galileo made a number of sunspot observations, and this really gives us our first modern record of sunspots from the scientific perspective. Now, there are times where we get more sunspots than at others. Times where our sun is particularly active and we have lots of sunspots, we call that a solar maximum. Now, what do we mean by active? That means our sun's magnetic field is quite active. In other words, it's breaking up, forming into different connected bands, and that ends up producing more sunspots. It turns out that when our sun is active, it also is slightly hotter than normal, and this can lead to small but not unmeasurable differences in the average temperature around the globe on Earth. Now, this is not something that would account for global warming. In particular, this being 2020 when this video is being made, the temperature of Earth has been a bit warmer than normal over the past several years. In fact, as we speak, the temperature of the globe is about half a degree over the average over the past decades, and this is a bit unusual because right now we're at a solar minimum. I would show you a picture of our sun right now and its sunspots, except it would be very boring. There are no sunspots on our sun right now. We are at a solar minimum. So it's relatively rare to be at a solar minimum and have such a bigger than average result for the global average temperature. In fact, it has never been this warm at a solar minimum. So that's something interesting to consider there. The typical time between solar maxima, successive solar maxima, the period, the sunspot oscillation period, is about 11 years. Sometimes it's a little more, sometimes a little less, but on average it's 11 years. So this is, on the right side, a picture of our sun around solar minimum, during the solar minimum in 2004. And on the left side is a picture of our sun at solar maximum. Look at all the sunspots. Now you might wonder, how is it that our sun is actually a little bit hotter during a solar maximum if you have these sunspots here? Well, remember that energy has to go somewhere. And you might notice that in the area around some of these sunspots, it is quite bright. These are what we call solar faculae. A facula is kind of the opposite of a sunspot. It's kind of where that extra energy goes after it's being deflected by the stronger than normal magnetic field. And overall, when our sun is active, the extra brightness from the faculae is more than cancels out the darkness of the sunspots. So again, here's a zooming in where you can see the sunspot itself, and also you have these granules around. And you have similar vocabulary for describing sunspots as for describing eclipses. The central dark part is called the umbra, and this kind of lighter area around it, formed by the magnetic fields and everything, is known as the penumbra. So the sunspot cycle, as I mentioned before, is an 11-year cycle, but there is actually a 22-year cycle as well. Now, why do these cycles occur? The sun, as we mentioned, rotates. We also mentioned that it has differential rotation, in that the equator rotates around faster than the poles. And by faster, I mean that the period of rotation at the equator is shorter than around the poles. So around the equator, it rotates about once every 25 days. Around the poles, it's about once every 34 days. So the actual length of the solar cycle is 22 years. Well, how does all of this tie together? This differential rotation, the fact that it's rotating faster around the equator than around the poles, ends up dragging around the magnetic fields in the sun. Because remember, these sunspots are caused by areas where our sun's magnetic field is particularly strong going into the surface, and it's like, okay, fine, everything's lined up right over here, but since things have a shorter period going around at the equator, things get stretched out, and the magnetic field lines get stretched out as well, because one of the laws of magnetohydrodynamics is that magnetic fields get tied in with plasma, and when the plasma shifts around, the magnetic fields end up getting shifted around as well. So if you start off in this situation, then after a while these magnetic field lines are going to get bent around like so, and then they're going to get very strongly bent around by like this, and the energy of that's going to be strong enough that occasionally the magnetic field lines are going to pop out of the surface, and it's when that happens that you often end up getting sunspots. In fact, it's because of that that you tend to get sunspot pairs. Looking back over here, in particular here, I'm looking at a nice little sunspot pair. That's because you have magnetic field lines popping out and then going back into the surface. So one of those is going to be a north end and the other is going to be a south end, just like a bar magnet. So the solar cycle is every 22 years, but the sunspot cycle is every 11 years. Now, the places that the sunspots occur tends to change depending on how active the sun is. In fact, if you were to plot those as a function of time, you get these nice little shapes that we call that a butterfly diagram. So you can go into that explanation a little bit if you want. You can pause the video, but in this situation we're actually just going to move on to talking about the solar output. Though before doing that, want to mention why it's a 22-year solar cycle versus an 11-year sunspot cycle. So after we get all of these sunspots appearing and everything, once the magnetic field lines get bent around particularly strongly, what ends up happening is things end up stabilizing when our sun's magnetic field reverses, and what had been the North Pole here becomes the South Pole. So the South Pole ends up being up top, and by top I'm talking about the direction of viewing it where our sun is rotating counterclockwise, and what had been the South Pole ends up becoming the North Pole. So, and when that happens, you have the same situation we have right here, except the magnetic field lines are going the other way, and then the cycle repeats, and then 11 years later you end up getting more sunspots again until the magnetic field reverses again. So the solar cycle is the time that it takes to go from north and south as viewed on top, with the north end being the point viewed from our sun rotating counterclockwise, to the south, that happens after 11 years, and then back to north, which is a total of 22 years. So the sun's solar cycle is 22 years, but the sunspot cycle happens every time the magnetic field is about to flip, and that's every 11 years. So, as we've mentioned before, when our sun is very active, the amount of energy being released by the faculae more than cancels out the lack of energy being released in the areas of the sunspots, where the sunspots are cooler and therefore radiate less energy. So yeah, overall, when our sun is active and you have lots of sunspots, the actual total emission from our sun is more, especially in areas like the ultraviolet parts of the spectrum and everything. So here's a picture of some of these faculae. This is a screenshot that I took actually in a lab that we did in one of my classes years ago. And you can see both sunspots and the faculae. This was taken from a hydrogen alpha camera and just shamelessly pulled off of this website, which unfortunately is no longer in operation. So the next thing to discuss will be the results of especially a particularly active sun. Our sun is always emitting something called a solar wind, but it also occasionally has more dramatic events, things like coronal mass ejections and solar flares. And those, along with the solar wind and the aurorae, are what we will talk about in the next video. So if you have any questions, please let me know, and stay tuned.